Okay, so we saw that sequence xn 1 plus 1 by 2 plus 1 by n. This sequence is monotonic increasing and not bounded above, so this sequence diverges to plus infinity, right? This we discussed last time. So now we'll discuss some special type of sequence and its convergence. So some sequences are very useful, right, for various purposes. So we'll discuss some of them, right? So have you seen the formula for compound interest? So this formula you just think about it. What is formula for compound interest? And then what is?
Sir, your screen is not visible.
Screen is not visible.
Yes, sir.
Screen is visible or not visible?
Sir,
Not
it's
visible, sir.
Just I will share it again. Okay, is it visible now?
Yes, sir.
Okay. Okay, so now we want to discuss limit of the sequence. Let xn is equal to 1 plus 1 by n raised to n. So this is a sequence. Now, what is our claim? Then, limit of this sequence is okay. What we want to prove this sequence converges. Then,
Sir.
x yes.
Hello, sir.
Yes.
Excuse me, sir.
Yes.
Sir, screen.
Screen दिसत नाही.
हो सर, स्क्रीन दिसत नाही.
Screen is visible or not visible? Some people can see the screen, right?
Yes, sir.
Yes, sir.
So it may be due to internet connectivity. So just check your connection. Right? Some people can see the
Okay,
screen.
sir.
Okay, so this sequence is convergent and 2 less than limit of xn is less than 3, and most important point is the limit of xn is e, an irrational number. Right, so and why I am saying this is a very important sequence, because you just go to the compound interest formula and then this sequence has something to do with it. Right. So to prove that this sequence is convergent, we'll first show that it is monotonically increasing. So xn is 1 plus 1 by n raised to n. Please keep your mic off. Abhijit, keep your mic off. Okay. Now, first we'll try to prove that it is monotonic, and then we'll check whether it is bounded out. Right. So 1 plus 1 by n raised to n. So you know that, just note it down. What is binomial expansion? Right? A plus b raised to n. And you know what is a binomial expansion? A raised to n, right? Plus n choose 1, n choose 0, n choose 1. N choose 1 is n into a raised to n minus 1 b, correct? N into n minus 1 upon 2 factorial a raised to n minus 2 b square, and so on. What is last? B raised to n. Is it correct?
Yes, sir.
Yes, sir.
Binomial expansion. Now, binomial expansion of the power is n, then it contains how many terms? Right. So binomial expansion has n plus 1 terms. For example, if you look at a plus b raised to 2, that means it is a square plus 2ab plus b square. So it has 3 terms. If you take power 3, then there are 4 terms, right? So n plus 1 terms. That is just here, because now xn is nth power of something. So now we will expand it by binomial expansion. So so by binomial expansion formula, what is xn? What is xn? How will you expand this? Right? How to expand this? What will be first term? 1, correct?
Yes, sir.
N into 1 by n. Right? This is n choose 1 plus n into n minus 1 upon 2 factorial, right? 1 by n square, right? N into n minus 1, n minus 2 upon 3 factorial, 1 upon n raised to 3. Just it n is 5, 6, whatever. So what is the kth term in this binomial expansion? This is
1 upon n raised to n.
so n, n minus 1, n minus 2 up to n minus k minus 1 upon k factorial 1 upon n raised to k plus plus. What is the last term, or what is second last term? Just binomial kth term. So first, second, third, and so on. So if I look at this term, in denominator it is k factorial, then numerator is n minus 1 up to n minus k minus 1. Right. So here it is 3 factorial, then n minus 1 n minus 2 into 1 upon n raised to 3. Right. So just continue this. What will be the last term and what will be second last term? Do you observe this terms? What will be last term? N, n minus 1, n minus 2. Here it will be n factorial, right? And here it is n minus 1. Actually, this is n factorial upon n factorial, which is 1, that we know, n raised to n, but I am writing it due to some reason. Correct?
Yes, sir.
Yes.
Right. So expansion is clear. Just binomial expansion. So 1 plus this n and this n get cancelled. So what remains? 1 plus 1 plus. Now next term. In next term, in numerator you can take n outside. So we'll have n square. 1 minus 1 by n. You just keep track of calculations. If any mistake, you just inform me. Right. So in next term, you can take n cube from the numerator. Right. And what would be the brackets now? Right. So you just check whether it is correct. So what about kth term? What power of n we can take outside from the numerator?
K.
So n raised n to the power k, 1 minus 1 by n, 1 minus 2 by n, n minus k minus 1 by n, right? So whole divided by k factorial into 1 upon n raised to k and so on. This is just in between some k term, right? Suppose n is 100 and just k is 65, like. So what about the last one? You understand, last term is just 1 upon n raised to n, but I am just writing in this pattern so that numerator is also n factorial and denominator is n factorial. It is n choose n, right? N choose n is 1. So what power of n I can take in numerator?
N raised to n.
N raised to n, right? So n raised to n, that power I can take here. And so what is it? 1 minus 1 by n, 1 minus 2 by n, 1 minus n minus 1 by n, whole divided by n factorial into 1 upon n raised to n. Right. So whatever calculations I am writing, not very difficult, right? Okay, so now our expression becomes simple. Plus, from this term, third term, n square get cancelled, right? So n square get cancelled. So what remains? Yes, correct. From fourth term, n cube get cancelled. And continue in this way. All successive terms you can understand. 1 upon k factorial. One minus, okay, here 1 minus. So 1 minus k minus 1 upon n. Right. And what about last term? What about last term? What about last term? 1 minus. Okay, so this is what xn is, right? So we have just simplified xn. So is it clear?
Yes, sir.
Yes, sir.
This is xn. Now from this, can you write down xn plus 1? Right, suppose you know the formula for nth term. This is a some expanded formula for xn. Can you write down xn plus 1?
Yes, sir.
Right, so what will be xn plus 1?
So we'll replace n by n plus 1.
Right, we have to replace n by n plus 1. Moreover, xn is 1 plus 1 by n raised to n, right? So xn plus 1 is 1 plus 1 by n plus 1 raised to n plus 1. So the power is now n plus 1. So how many terms will be there in binomial expansion?
N plus 2.
Right, n
N
plus,
plus 2.
right. So therefore, uh, let us write down formula for xn plus 1. Just uh, take reference of xn and then what will be the formula. So first terms 1 plus 1 is same in any case. What is next? 1 minus 1 upon n plus 1, right? 1 upon 3 factorial, 1 minus 1 upon n plus 1, 1 minus 2 upon n plus 1, and so on. What is some kth term in between? 1 upon k factorial, 1 minus 2 upon n plus, just replace n by n plus 1 and so on. What would be the last term and what would be second last term? Right, what will be last term and what would be second last term? 1 plus 1. So in this term, 1 upon 3 factorial and so on. In k term, 1 upon k factorial into something. Right, so what is the last term for xn plus 1?
1 by
1
n plus factorial.
n plus 1 factorial into, just compare the last term of xn. 1 upon n plus 1 factorial into, what is the bracket? 1 minus 1 upon n plus 1, 1 minus 2 upon n plus 1 into, what is last bracket in last term? What would be last bracket in last term?
1 minus n plus 1 minus 1 by n.
Right. 1 minus n plus 1 minus 1 means n, right?
Yes,
Correct.
sir.
What is now second last bracket? Right. So this bracket, last bracket.
Last term of xn.
So this term corresponds to n plus 1. So second last term corresponds to n, right? So therefore it is 1 upon
Yes,
n.
sir.
Sorry, 1 minus 1 upon n plus 1, 1 minus 2 upon n plus 1, up to 1 minus n minus 1 upon n plus 1. Right, so this is second last term and this is last term. Okay, so this is a big expression for xn plus 1. So let us call this as 1. Let's call this as 2. Right. Okay, so expression 1 and 2 are clear now.
Yes, sir.
Yes, sir.
So there is no confusion among these two expressions, xn and xn plus 1. And one observation is xn has n plus 1 terms, xn plus 1 has n plus 2 terms. Right. So xn plus 2 has n plus 2 terms xn has xn plus 1 terms. So these two things you should remember. Correct. Now note that for 1 less equal k less than n, 1 minus 1 k upon n is less than or equal to 1. Am I right? Right. And so that this is true for each n, right? In fact, this is true for n plus 1 also. 1 less equal k less than n plus 1, less than or less equal, no problem. In any case, 1 minus k upon n plus 1 is less than or equal to 1. Right, so 1 minus something which is a positive quantity. So 1 minus some positive quantity is less than 1. So that is clear for whatever k in the, and therefore 1 minus 1 by n less equal 1, 1 minus 2 by n less equal 1, 1 minus 3 by n less equal 1, and so on, right? All these brackets are less equal 1. Also 1 minus 1 upon k plus 1, 1 n plus 1 less equal 1, 1 minus 2 upon n plus 1 is less equal 1. Whatever is, all such brackets are less equal 1, right? Therefore from okay, this is one observation. One more observation. Second observation is, if you compare for k less equal n, right? What is the relation between, so n plus 1 is greater than n, correct? Therefore 1 upon n plus 1 is less than 1 by n, correct? And if you multiply by k, right? Yes.
Yes, sir.
So minus k by n is less than minus k by n plus 1. You just check whether I am writing correctly. Add 1 throughout is less than, yes, is it correct?
Yes, sir.
So therefore 1 minus 1 by n and 1 minus 1 by n plus 1, which is bigger quantity? Second one, right? And 1 minus 2 by n plus 1. Second one is bigger quantity, right? And so on. So, okay, so why these numbers are important? These brackets are important. So we want to compare xn and xn plus 1, which is bigger, right? We want to compare xn and xn plus 1, which is bigger. Okay. Now, if we compare this third term of xn and third term of xn plus 1, which is bigger. This is third term of xn and third term of xn plus 1. Which is bigger now?
Third term of xn plus 1.
Right. Right. So now look at fourth term. These two brackets, product of these two brackets, and here product of these two brackets. So which is bigger now? Xn plus 1. Third term of xn plus 1. Correct? Just compare term by term. Just compare term by term. So first term of xn, and so just compare the term by term. So first term of xn, xn plus 1, xn, xn plus 1, just compare. That is what I am doing. So I am just comparing. For kth term, look at any kth term of xn and xn plus 1. So look at kth term of xn and xn plus 1. So xn plus 1 kth term is. Now look at last term of, because xn has n plus 1 terms. So last term is n plus first term. And then compare the brackets, right? And that corresponds to second last term of xn plus 2, xn plus 1, right? This is bigger.
Yes,
Right?
sir.
Now, if you compare term by term, then in xn plus there is additional term. Right? If you compare term by term, first term, second term, then in xn plus 1 corresponding terms are larger. Moreover, in xn plus 1 there is one additional term. And therefore, which is therefore from 1 and 2, expansions of xn and xn plus 1. 1 is what? Expansion of xn. 2 is what? Expansion of xn plus 1, which is bigger. We observe that which is bigger.
Plus 1.
Right? And is it true for all n?
Yes, sir.
This is true for all n. Very good. Therefore, can I say that xn is monotonically increasing?
Yes, sir.
So is this clear? How did I compare the terms? Right. So I just compare term by term. First term of xn plus 1 and first term of xn. So xn plus 1 is bigger, and in addition to that, xn plus 1 has one more positive additional term, which is the last term, n plus second term. So this is an additional term. Therefore, xn plus 1 is very bigger, still bigger than xn. So this sequence xn is monotonically increasing. So now what we should look for? What we should look for now?
That it is bounded above or not.
So we should look for whether it is bounded above or not. So okay, so we'll try to check whether it is bounded above. So for this, let us take xn again, look at xn, and from that we'll try to check whether there is a number which is bigger, right? So okay, so okay, what I want to carry xn again so that we can observe whether it is bounded above. Okay, so now we will try to find out upper bound for this. Okay, so from 2, from 1 we have this. So next we will check whether xn is bounded above. Okay, so now let us check whether it is bounded above. So this is xn, which we already calculated, right? I have just taken it forward. So since 1 minus 1 by n is less than 1, 1 minus 2 by n is less than 1, right? So 1 minus k by n is less than 1. All these brackets 1 minus n minus 1 upon n is less. All these things are less than 1, right? Therefore, what I can say, xn, which is 1 plus 1 plus 1 upon 2 factorial 1 minus 1 by n, 1 upon 3 factorial 1 minus 1 by n into 1 minus 1 up 2 upon n and so on. What is last one? 1 upon n factorial 1 minus 1 by n, 1 minus 2 by n, 1 minus n minus. Right, so this is our xn. But we know that all these brackets are less than 1. Therefore, if I take 1 as it is, this 1 as it is, now if I replace this bracket, right, if I replace this bracket by 1 and 1 upon 2 factorial as it is, 1 upon 2 factorial as it is, and I will replace this bracket by 1 plus 1 upon 3 factorial as it is. I will replace these two brackets by 1. So 1 upon n factorial as it is, I will replace these brackets by 1. So which quantity is larger?
Second one.
Second quantity.
Right? So this quantity is larger because I am just replacing brackets by 1 and brackets are less than 1. That's it, right? Fine. Further, observe that 1 upon 3 factorial is 1 upon 3 into 2, right? And I am replacing 3 by 2. In 3 factorial, 3 and 2, I am replacing 3 by 2. So which quantity is larger?
Right hand side.
Second one.
So second quantity is larger. Alright. So similarly, what about 1 upon 4 factorial? And I have here 4 factorial means what? 4, 3, 2, 1. Right. And I am here writing replacing 4 by 2, 3 by 2, 2 as it is. And then this quantity is larger. So 1 upon 2 raised to 3. Right. So in general 1 upon k factorial. And here I have 2 raised to k minus 1. So this quantity is larger. Correct?
Yes, sir.
Yes, sir.
And now we are here. Xn is, let us call this as expression 3. From this, so from expression 3, xn is less equal 1 plus 1 plus 1 by 2 factorial plus 1 by 3 factorial plus 1 by 4 factorial up to 1 by n factorial. This is our previous expression, right? We saw that xn is less than or equal to this. This already done, but from this previous inequality, 1 as it is, 1 as it is, 1 by 2 factorial is 1 by 2. Now I am replacing 1 by 3 factorial by 2 raised to 2. Right? Do you understand? I am replacing 1 by 3 by 1 by 2 raised to 2, 1 by 4 by 1 by 2 raised to 3, and 1 by n by 2 raised to n. Which quantity is larger now? Do you understand? Compare the terms, corresponding terms. 1 by 2, 1, 1, and second one. Because we have just seen 1 by 3 factorial is less than 1 by 2 raised to 2. 1 by 4 factorial is less than 1 by 2 raised to 3. Right? So 1 by k factorial is less than 1 by 2 raised to k minus 1. So 1 upon n factorial is less than 1 upon 2 raised to n minus 1. So second quantity is larger. Fine. 1 plus. Okay. So look at this part. What is this?
Geometric progress.
Geometric, right? Geometric sum. 1 plus r plus and What is r in this case?
Half.
1/2.
1/2, right? And therefore, what is the sum? Correct?
1/1 minus 1/2.
1 minus 1/2. So 1 minus 1/2 raised to half raised to n, correct? Because just the geometric sum is 1 plus r square r raised to n. What is it? 1 minus r raised to n plus 1 divided by 1 minus r. Do you know this formula?
Yes, sir.
Right, same formula I am just applying here. R is half, and so it is equal to this. So this is equal to 1 plus. So 1 minus half is half. So it is 2 times. Yes, is it correct now?
Yes, sir.
Therefore, where we are now? We are at the situation where we see that xn is less equal 1 plus 2 times 1 minus 1/2 raised to n. This is the situation, current situation. So observe that 1 upon 2 raised to n, 1 upon 2 raised to n is a positive quantity, correct? Whatever is n.
Yes, sir.
And 1 minus 1/2 raised to n is less than 1. Whatever is n, no problem, correct? Therefore xn, which is less equal 1 plus, can I say that this amount is less than 1 plus 2, which is 3?
Yes, sir.
Right, so this is true for all n, no matter what n you select, because we just selected arbitrary term xn and we found that it is less than 3. Right, therefore xn is less than or equal to 3. In fact, it is strictly less than 3, but anyway, for all n. Therefore, can we say that xn is bounded above?
Yes, sir.
Xn is bounded above. Sequence xn is bounded above. And thus, xn is monotonic increasing bounded above, and hence what? Convergence. Right, so now this sequence is convergent. Okay. Further, so if you look at xn, uh, if you look at xn, then what can you say about this xn? This is xn, right? Xn is this. Is it clear?
Yes, sir.
Now, in this expansion of xn, if you look at the terms, all terms are positive. Right? Do you understand? Ki, if you look
Yes.
at first this term, if you look at this term, or all terms are positive. Suppose we delete. Can I say that from this can I say that therefore xn is greater than 2? Greater than 2
Yes,
means what?
sir.
Yes,
Why it is greater than 2? It is greater than 1 plus 1. 1 plus 1 means this one and this one. And suppose I delete this term. So whatever quantity I will get this 2. This is true for all n. Therefore, 2 and xn is less than 3 for all n. Right? 2 less than xn less than 3 for all n. Therefore, what can you say about limit?
Limit lies between 2 and 3.
Right. Therefore, 2 less than or equal to limit of xn is less than or equal to 3. Right. So limit of this sequence lies in between 2 and 3. This is what the point is. Okay. So we proved that sequence is convergent, and we also saw that limit lies in between 2 and 3. So limit of this sequence is denoted by a symbol E. Right. So the limit of this sequence is denoted by symbol E. The number E is a real number right. So this number is a real number which is not, which is an irrational number. So this number, what is E? What is number U? You must have used number E before in calculations. Have you used the number E somewhere in physics?
sir.
Yes. And what is that number E? It is actually a number which is limit of this sequence. And that number is not a rational number, it is irrational number. Right, and therefore this sequence converges to an irrational number. That number limit of this sequence is called as E. Right, limit of this sequence is called as E. So
But this number only between 2 and 3.
why? What?
Sir, why only this number? It can be anything, no?
No. What are xn? Xn lies in between 2 and 3. So limit is in between 2 and 3.
Sir, but actually this number is 2.71 something. So
Yes.
like it can be anything, no? Why is it so that it is E only?
Why it is means what? It is a number where this sequence converges. That point is called as E.
Okay, sir.
Right? Where this sequence converges. So in between 2 and 3, this sequence converges at some point, and that point is called as E. So the name came after this kind of things. People found that there are sequences of rational numbers. See, each xn is a rational number. Do you observe this? Is a rational number for all n. Each xn is a rational number. So what people found ki there are sequences. See, initially people believed that ki only rational numbers are sufficient. Right? What people believe ki you can fill this entire real line by rational numbers. That was the perception. But then people found that no, this is not true. We can have a sequence of rational numbers which do not converge in rationals, right? So we can have a sequence of rational numbers, and sequence is convergent, that is clear, because increasing bounded above. And what completeness property says, it must have a supremum, and supremum is a real number, so it converges to supremum, right? So that supremum must be a real number, and therefore limit must be real number, right? So this sequence converges to some number, but that is not rational number, but it is a real number. So where it is, so that number is not missing, so they included those numbers in the system of real numbers, and this number is a spatial, so the name is given the spatial name. There are many rational numbers, but this number is a very special due to some reasons, because this number is used at several occasions. And there is one more number which is irrational number and which is a very special number, which is, what is that number?
Pi.
Right, pi e. These are special numbers. That's why the number names or symbols are given them. Right, there are many other irrational numbers, but these two are special, right? Now, why this number is irrational, that can be proved, right? And this could be a project. If some student is interested, one can do a project. You will get internal marks for that. What could be the question? Why E is irrational number? That means why limit of this sequence is irrational number. Limit is some number E. We know limit exists. That number, that point is E. We are sure that there is a number which is a limit of this sequence. We are calling it as E, but that number is not a rational. That is a question. Why it is not rational? Right? Why pi is and is not a rational number? So these are two questions. You can take one of the question and get the detailed information, detailed proof, right? So you can think about it. Okay, so is it clear?
Excuse me, sir.
Yes.
Yes, sir. Actually, this number goes forever and ever. So, like the decimal point after that. So, like, what's the importance of these numbers, E and pi? Like
See, what is the point here? See, we proved that sequence is increasing,
yes, sir.
and therefore, so do you see the picture I am drawing here?
Yes, sir.
So, and moreover it is bounded above, so no problem. So terms are increasing, and since it is bounded, the terms will settle at some point. But what is at that point? We cannot get hold of that point. We cannot catch exactly that point.
Okay, sir.
Right, and therefore, if you go, if you look at the 100 term or 1000 term, be very close to that number. Right, if you look at x100 and x150, x50 is very closer, more closer to E than x100. Do you understand this?
Yes, sir.
And
Sir,
this,
but actually the limit, why does it E is the numbers after the decimal point, it goes increasing, increasing, increasing. Then why, sir, we chose only E and not any other number?
see, that's why I said in the beginning, if you look at the compound interest formula, right,
Yes, sir.
or exponential growth or decay of radioactive compound, and then what is the growth or decay rate of radioactive compound? It is exponential.
Yes, sir.
Population growth, it is exponential. So exponential, E is important because the many phenomena taking place in the real life or in the universe, the rate of change is exponential, and therefore E is important.
Okay, sir.
Right? Okay, and why we are studying this sequence? Because we can approximate value of E by just calculating the higher and higher terms, x50, then x500. x500 is very close to E. That means error between E and x500 is less, right? Error between E and x500 is less. But if you calculate error between E and x2000, it is very less, so we can get more and more approximate value of E. And where we need approximate value, if you are doing some experiment and you want to you are expecting some outcome, and in that calculation you are using value of E, then which value you should use so that you will get more accurate expected answer. Your calculations are very closer to the expectations. Which value of you should use? Understand? If you use more accurate value, you cannot take exact value of E because E is irrational number. But you can, if you take x500 and if you take x2000, x500 is a closer value, but x2000 is very close. And therefore, if you take x2000, that value of E, then that will give you better answer, right?
Sir.
Same thing is for pi. Generally, we use 22/7, but 22/7 is not a value of pi. 22/7 is a rational approximation of pi. Approximation. It is not correct value, right? That means 22/7 is a value near actual value. So there are many approximations of pi. Many people did research by different using different techniques to get approximate value of pi. And if you take more approximate value, that will give you the more desired result. That's why. So right now we are just interested in convergence and all these things, but in future we are going to use these facts to solve some real life problems. Which value, which approximation is better, right?
Yes, sir.
Okay, so you think about it, you go through the proof again, read the proof detail, write down it again in your notebook. Then next time we'll see some more problems, right? So any doubts?